Tonight, we're going to listen to a very soft question hiding inside a very large universe. Is the cosmos the same in every direction, or is it slightly tilted? This is a calm, documentary-style analysis and synthesis of astronomy and cosmology research. If you use visuals for this episode, treat them as AI/CGI scientific visualizations, not real footage. Where we step into speculation, I'll label it clearly as a hypothesis or a possibility, not a conclusion. Now, let's begin with something most cosmologists agree on. On the largest scales, the standard model of cosmology assumes the universe is statistically homogeneous and isotropic. In plain words, averaged over huge distances, it looks roughly the same in everywhere and in every direction. That assumption is not just philosophical, it is practical. It lets us build models. It lets us interpret surveys. It lets us turn a sky full of galaxies into a coherent story. And yet, even in that same in every direction picture, there is one very prominent exception. The cosmic microwave background, the afterglow of the early universe, has a dipole. One side of the sky is slightly warmer. The opposite side is slightly cooler. This is the strongest anisotropy in the microwave background, and it is usually interpreted in a simple human way. We are moving. If you move through a bath of radiation, you see it slightly blue shifted in the direction you're traveling and slightly red shifted behind you. That creates a dipole pattern. It's the same reason rain feels like it comes more from the front when you run. In the standard interpretation used by missions like COBE and Planck, the CMB dipole is mainly kinematic, a velocity effect. It implies that the solar system is moving at a few hundred kilometers per second relative to the CMB rest frame in a specific direction on the sky. So far, this is not an anomaly, it is a foundation. But here is where the quiet tension begins. If the CMB dipole is mostly due to our motion, then other tracers of the universe, galaxies, quasars, radio sources, should show a matching dipole. Not necessarily identical in every detail, because matter is clumpy and surveys have limitations, but broadly consistent. This idea is sometimes discussed through what's called the Ellis-Baldwin test. You look for a dipole in the number counts of distant sources created by our motion through the cosmic rest frame. And over the last decade, multiple analyses have suggested something intriguing. The matter dipole inferred from some surveys can look larger than the kinematic expectation derived from the CMB dipole. In direction, the dipoles often point roughly the same way, but in amplitude, some measurements appear too big. This is what people mean by the cosmic dipole anomaly. Not a claim that isotropy is broken beyond a doubt, not a claim that the universe is secretly different, but a persistent, measurable tension between dipoles inferred from different datasets. Tonight, we will handle this carefully. We will talk about what the dipole is and why motion creates it, how surveys try to measure a matter dipole, why systematics and survey geometry can mimic or inflate dipoles, what the most cautious interpretations look like, what kinds of new physics have been proposed and why those ideas are still tentative, and what future surveys may clarify. And along the way, we'll keep the pace slow. No urgency, just curiosity. A small question before we move on. When you imagine the universe, do you instinctually imagine a perfectly uniform cosmic ocean, or something with a subtle slope? If you'd like, tell me what your intuition says in the comments. Now, let's start with the simplest part: why motion creates a dipole and why the CMB is the cleanest place to see it. Before the microwave background was even discovered, scientists debated what the word cosmos should imply. Some imagined a universe with a center. Some imagined a universe with edges. Some imagined a universe shaped by symmetry where no direction is privileged. Over time, the no special place idea became known as the Copernican principle. And in modern cosmology, it grows into the cosmological principle. On large enough scales, the universe is homogeneous and isotropic. But notice the careful phrasing: on large enough scales and statistically. This is not the claim that every direction is identical in a literal sense. We already know the nearby universe is uneven. We have galaxy clusters and voids. We have superclusters and filaments. We have a Milky Way that dominates our local sky. Statistical isotropy means something gentler. If you blur your eyes enough over truly enormous distances, the distribution of matter and radiation has no preferred direction in its statistics. That is why the dipole question is so interesting. The dipole is the largest scale directional signal we can easily measure. If it behaves as expected, it supports the quiet symmetry of the standard picture. If it behaves unexpectedly, it might be warning us about measurement challenges or hinting at deeper structure. Either way, it is worth listening to. And there is a reason this topic fits a sleep-friendly channel. It is not about danger. It is about orientation. It's a compass question, not a crisis question. So we will keep the mood soft, and we will keep the words honest. Now let's continue into the physics of motion and the dipole, one slow step at a time. To understand the dipole, you don't need heavy equations. You just need a gentle picture of light and motion. Imagine the universe filled with a uniform fog of radiation. If you are at rest relative to that fog, it looks the same in every direction. If you move, the fog becomes slightly brighter in the direction you're heading. That happens because of two related effects: Doppler shifting, which changes the frequency of the radiation, and aberration, which changes the apparent direction of incoming photons. Together, they create a dipole, a single warm direction and a single cool direction. For the cosmic microwave background, this dipole is extremely well measured. It dominates the CMB sky map. And because the CMB is a clean early universe signal, it provides a natural definition of a cosmic rest frame. In the standard interpretation, our velocity relative to that frame is about a few hundred kilometers per second, and the dipole direction is well established. Now, if that's true, then in principle, the same motion should affect the observed distribution of distant objects. This is where the Ellis-Baldwin idea enters. If you move through the universe, your motion changes how many sources you see in different directions for two reasons. First, aberration slightly changes the solid angle, making sources appear more concentrated in the forward direction. Second, Doppler boosting changes observed flux densities, nudging more sources above a survey's detection threshold in the forward direction. So a flux-limited survey of radio galaxies, for example, should show a dipole in number counts aligned with the CMB dipole. But here is the crucial nuance. Unlike the CMB, matter is clumpy. Galaxies are not smoothly distributed. There are structures, clusters, superclusters, voids, filaments. And surveys have masks, calibration issues, and incomplete coverage. So when we measure a matter dipole, we are mixing multiple contributions. A kinematic dipole due to our motion, a clustering dipole due to real large-scale structure, and potential biases from survey systematics. In many analyses, the puzzle is not the direction. The direction often comes out broadly consistent with the CMB dipole. The puzzle is the amplitude, how large the dipole seems compared to the kinematic expectation. Radio surveys have been an important part of this story. For instance, number count dipole analyses of the NVSS catalog have historically found amplitudes larger than expected from the CMB-based velocity, though the interpretation depends on careful modeling of clustering and systematics. Quasar catalogs, especially infrared selected samples, have also been used to estimate dipoles, and some results have reported a tension with the kinematic expectation. Recent review-style discussions emphasize that the direction agreement is notable, but amplitude differences require caution and careful uncertainty accounting. Now at this point, it can be tempting to jump to conclusions, but the calm scientific posture is different. The calm posture is to treat the dipole anomaly as a diagnostic, a sensitive test of survey systematics, modeling assumptions, and, only if needed, new physics. So our next step is to walk through how dipoles are actually measured and why measurement choices matter. Because in dipole work, small choices can produce noticeably different amplitudes. And that is not a scandal. It is the normal reality of doing precision cosmology with real-world data. Here is a gentle example. Suppose you measure a dipole from a catalog. You must decide how to mask the Milky Way plane, how to treat bright local sources, how to handle varying depth across the sky, how to correct for declination-dependent calibration, which flux cuts to use, and how to model the redshift distribution and clustering. Each decision can shift the answer. So the anomaly is not one number, it is a landscape of analyses. If you're still listening, consider this question. When you hear that different surveys disagree, do you assume someone is wrong, or do you assume the measurement is hard? You can share your instinct in the comments. Now, let's get closer to the measurement itself, the practical art of turning a sky map of sources into a dipole vector. It can help to remember that the CMB is not just any background. It is a snapshot of the universe when it was young, hot, and nearly uniform, long before stars and galaxies formed. When scientists map the CMB, they usually separate the sky into patterns of different angular sizes. The dipole is the largest pattern, one warm side, one cool side. After subtracting the dipole, they study smaller patterns, the ripples that tell us about early universe physics. So the dipole is both an observable signal and, in practice, a calibration anchor. Historically, the dipoles measured by missions like COBE and then refined by later experiments and Planck's full sky maps. Across these efforts, the dipole's interpretation as a motion signal has remained robust, even as the details of calibration and map-making improved. That's why the CMB dipole is often treated as the gold standard direction and speed for our motion relative to the observable universe. Now, it might seem odd to talk about speed in space, since everything is expanding. But this speed is not about expansion. It's about peculiar motion, motion relative to the average cosmic flow. Our local motion has a layered story. The Earth orbits the Sun orbits within the Milky Way moves within the local group, and the local group moves relative to the CMB frame, influenced by the large-scale gravitational landscape around us. So when we speak of a kinematic dipole, we are speaking about motion embedded in a clumpy universe. And this is the key tension. The dipole we measure in matter tracers is not pure motion. It is motion plus clumpiness, plus the survey's personality. If you keep this in mind, the dipole anomaly becomes less mysterious and more like an intricate measurement puzzle. Now, let's go one layer deeper into how a survey's personality can become a dipole. A dipole measurement, at its core, is a way of asking, is there a preferred direction in my data? For a source catalog, one common approach is to treat each source as a point on the sphere, then estimate the best fit dipole direction and amplitude that describe an excess of sources in one hemisphere compared to the opposite. Some methods work directly with number counts. Others weight sources by flux. Some use spherical harmonics. Some use Bayesian estimators that model uncertainties more explicitly. The details matter because the dipole is a low-order signal. It is large in angular scale, and low-order signals are particularly vulnerable to sky cuts, survey geometry, and large-scale gradients in depth or calibration. This is one reason the Milky Way is such an important complication. The galaxy is bright in many wavelengths. Surveys often avoid the plane or mask it. That creates a missing strip of sky. When you remove a large region, you can unintentionally couple different spherical harmonic modes, altering the apparent dipole. In a calm way, you can think of it like trying to infer the center of a circle while a chunk of the circle is hidden behind a curtain. Now let's talk about a second complication: local structure. Our local universe is not average. We live in a region with known large-scale structures. Those structures can produce a real clustering dipole, a genuine asymmetry, because nearby overdensities contribute more strongly. This is why some dipole studies focus on very distant sources, like high redshift quasars. The farther the sources, the less local structure should matter. But even there are subtleties. The redshift distribution might not be perfectly known. The selection function can vary across the sky. And dust extinction or scanning strategy can leave large-scale patterns. So an observed quasar dipole can include both cosmological signal and survey imprint. This is exactly why recent reviews and analyses emphasize careful modeling of uncertainties and systematics when interpreting any excess dipole. Now, what do scientists do to handle this? They simulate. They create mock skies that include the expected kinematic dipole from our motion, realistic clustering consistent with a cosmological model, shot noise from finite source counts, and the survey mask and selection function. Then they run the same dipole estimator on the MOCs. This allows them to ask, if the universe is standard and our motion is the CMB inferred value, how often do we measure a dipole as large as the one in the real catalog? If the answer is rare, tension grows. If the answer is not so rare once you include all uncertainties, tension softens. This is why the cosmic dipole anomaly is not a single fixed headline. It is an evolving dialogue between data and modeling. Now let's pause on a concept that often hides behind the scenes: shot noise. Shot noise is the uncertainty that comes from counting discrete objects. If you have 1,000,000 sources, shot noise is smaller than if you have 10,000. But shot noise is not the only counting uncertainty. Clustering also adds variance. Because sources are correlated, they come in groups and filaments rather than independently. So the expected dipole distribution has width. The anomaly is about whether the measured amplitude sits far in the tail. In radio catalogs like NVSS, the community has debated how to model clustering contributions and how much they reduce the apparent discrepancy with the CMB. In infrared quasar catalogs, similar debates revolve around selection function gradients and how best to represent the true underlying distribution. Now, to keep our tone gentle, let's put this into a quiet story. Imagine you are trying to measure a slow breeze by watching leaves on a large field. Some leaves move because of the breeze, but some move because of tiny local vortices. Some fields have uneven terrain. Some corners are shaded and you can't see the leaves there. If you see more leaf motion in one direction, is it a global breeze or a local pattern or a problem with your visibility? This is the dipole problem in a nutshell. You are extracting a global, low-order pattern from data that is clumpy, incomplete, and sensitive to systematics. So, what have researchers found? A cautious summary, consistent with multiple review discussions, is this. Many matter dipole measurements broadly align in direction with the CMB dipole. Some show amplitudes higher than the kinematic expectation. The extent of the significance depends strongly on how clustering, shot noise, and survey systematics are modeled. That is the landscape. Now, in the next file, we'll step into the specific categories of systematics that can mimic a dipole: calibration gradients, declination dependence, stellar contamination, dust extinction, and masking. If you are still awake, here is a simple engagement question. When you hear systematics, do you think of it as an excuse or as a normal part of precision science? Comment below. Your answer tells me how much background to include in future episodes. Now, let's move into the quiet mechanics of bias and how it can shape a dipole without anyone intending it. There are also choices about weighting. If you count each source equally, you are measuring a dipole in number density. If you weight by flux, you are giving brighter sources more influence, which can change sensitivity to local structure and calibration errors. Different choices can be useful for different reasons, but each choice has trade-offs. Another subtlety is the difference between full sky and part sky estimators. On a perfect full sky, spherical harmonics separate cleanly. On a masked sky, they do not. So analysts use techniques to correct for this: debiasing, in-painting, precess CL methods, or forward modeling in simulations. And even with the best techniques, there is a truth that remains. Low multipoles are hard, because low means global. Global patterns are exactly where any slowly varying systematic can hide. So dipole analysis is, in practice, an exercise in humility. It is also why dipole work can be surprisingly philosophical. It forces you to ask over and over, what do I truly know from the sky, and what is the sky telling me through my instrument? Now, one more ingredient, the clustering dipole. In a perfectly random distribution of sources, there is no intrinsic dipole. But the universe is not random. It is correlated. So even in an isotropic cosmology, a finite survey can show a clustering-induced dipole. This means the correct question is not, does the survey dipole match the CMB dipole exactly? The correct question is, does the survey dipole fall within the expected distribution once I include clustering, noise, and survey realism? That expected distribution is typically built through Monte Carlo mocks. When you read papers about dipole tensions, pay attention to how the mocks were built. What redshift distribution was assumed? How was the mask applied? Were calibration gradients injected? Was the clustering amplitude consistent with observed angular correlations? These details are not footnotes, they are the heart of the inference. Now, in the next file, we'll list the systematics again, but this time with a calmer intuition for how each one can create a dipole without anyone intending it. In precision cosmology, the most dramatic signals can sometimes come from the most ordinary causes. A calibration gradient, a scanning strategy, a threshold effect. These are not conspiracies. They are the real texture of observational work. So if we want to understand the cosmic dipole anomaly responsibly, we need to be fluent in systematics. Let's walk through a few common ones. First, varying depth across the sky. No survey is perfectly uniform. In a radio survey, sensitivity can vary with declination because of telescope geometry and observing time. In an infrared survey, depth can vary with scan coverage and background emission. In optical surveys, seeing and extinction can vary. If the survey is slightly deeper in one hemisphere, you will detect more faint sources there. That creates a dipole-like gradient. Second, contamination. In quasar catalogs, one challenge is separating quasars from stars and galaxies, especially at faint levels. Even a small contamination fraction that varies across the sky can imprint a large-scale anisotropy. Third, dust extinction and foregrounds. In optical and infrared surveys, dust in the Milky Way can reduce the apparent brightness of sources or alter colors used for classification. If extinction corrections are imperfect, a large-scale gradient can remain. Fourth, masking and mode coupling. When you mask the galactic plane or bright regions, you remove parts of the sky. The dipole estimator must then infer a global pattern from an incomplete sphere. If the mask is asymmetric or interacts with surveyed depth variations, the estimated dipole can shift. Fifth, flux calibration and spectral assumptions. In radio dipole analyses, Doppler boosting depends on source spectral index and the slope of number counts. If those inputs are misestimated, the kinematic expectation can be off by a meaningful factor. At the same time, instrumental calibration issues can create spurious large-scale gradients. Because of all this, modern dipole studies often include extensive null tests. Rotate the mask, split the catalog by flux and compare, split by observing conditions, cross-match with other surveys, and build detailed simulations. This is one reason recent work emphasizes careful tension quantification and reassessment, rather than treating any single estimate as final. Now, you might wonder, if systematics are so strong, how can a dipole measurement ever be trusted? The answer is by agreement across independent surveys with different systematics. Radio surveys and infrared quasar catalogs are affected by different foregrounds and selection effects. If both show an excess dipole in the same direction and of similar amplitude, that becomes harder to dismiss as a single survey artifact. However, the magnitude of that harder depends on whether the surveys share hidden common biases and whether the analyses model clustering consistently. This is why review discussions emphasize that direction agreement is important, but amplitude disagreements still require caution. Now, let's be very clear about a key integrity point. It is tempting when you see a tension to say, this proves the cosmological principle is wrong. But that is not the careful claim. The careful claim is, some dipole measurements appear to exceed the kinematic expectation under certain modeling choices. This could be due to underestimated systematics, underestimated clustering contributions, or, more speculatively, an additional intrinsic dipole component. The word could matters, and the difference between could and must is the difference between documentary analysis and sensationalism. So, in this episode, we will not turn attention into a verdict. Instead, we will map the plausible explanation space. And to do that, we should talk about the two main categories of explanations. Category 1. The dipole is mostly kinematic, but measurement systematics and clustering inflate the observed matter dipole. Category 2. There is an additional intrinsic anisotropy in matter on very large scales beyond the kinematic effect. Category 1 is conservative. Category 2 is more radical. Both are being discussed. Neither is settled. Now, before we explore Category 2, it helps to take Category 1 seriously, because in many cases, once systematics are modeled carefully, the significance of the excess can change. So the story is still active. If you'd like an engagement question here, do you prefer episodes that stay strictly conservative, or do you like hearing the speculative ideas as long as they're clearly labeled? Tell me in the comments. It helps me tune the balance. Now, in the next file, we'll explore the more adventurous side carefully. If there really is an intrinsic component to the matter dipole, what kinds of physics could produce it? We will treat these ideas as hypotheses. We will not treat them as truth. Let's step into that space gently. A helpful mental model is this. A dipole is a gradient. Anything that creates a gradient on the sky can masquerade as a dipole. For example, imagine a survey with a slightly different flux calibration in the northern sky than in the southern sky. If the catalog has a fixed detection threshold, that calibration offset changes how many sources land above the threshold. Suddenly, you have a north-south gradient, and a gradient looks like a dipole. Or imagine that the survey is deeper near the ecliptic poles because of scanning coverage. That can create broad regions with more sources detected. If those regions happen to line up in a way that projects onto the dipole direction, the estimator will happily report a dipole. This is why null tests matter. A null test is a way of asking, if this dipole were due to a known survey property, would it behave in a predictable way when I split the data? For example, if the dipole changes dramatically when you change a flux cut, it may be tied to threshold behavior. If it correlates with observing time or declination, it may be tied to coverage. If it correlates with dust maps, it may be tied to extinction or foreground subtraction. If it changes when you alter the galactic mask, it may be tied to mode coupling. None of these tests guarantees an answer by itself, but together they can reveal whether the dipole is stable or fragile. And stability is the quiet sign of something real. Now, in the next file, we'll keep our feet on the ground and talk about new physics only in the careful conditional way that cosmology requires.
If we assume, only as a working hypothesis, that some part of the matter dipole is not explained by our motion plus expected clustering, then we are forced to ask a deeper question. Could the universe have a preferred direction on the largest scales? In the standard cosmological model, statistical isotropy is a key assumption. But assumptions are tested, not worshipped. So the existence of a matter dipole metric naturally leads to what-if ideas. Here are a few of the main categories described gently. 1. A very large-scale density gradient. If the universe had a super-horizon scale mode, a fluctuation larger than the observable volume, then within our observable patch, matter density could appear slightly higher in one direction. That would create a dipole-like pattern in number counts. This idea has been explored in different forms, but it must satisfy strong constraints from the CMB and other observables, so it is not a free playground. 2. A difference between rest frames. The CMB defines a radiation rest frame. Matter, in principle, defines a matter rest frame. In a perfectly standard picture, those frames align on large scales. But one way to interpret a matter dipole larger than the CMB-based kinematic expectation is that the frames might not match as cleanly as assumed. Recent review-style discussions note this as a possible interpretation, though not a proven one. 3. An anisotropic expansion. In some modified cosmological models, expansion could be slightly anisotropic, meaning the Hubble flow could have directional dependence. That would be a major departure from the standard model. It would also need to be consistent with many other constraints, including the CMB and large-scale structure. At present, this remains speculative in the context of dipole tensions, and it is not the mainstream conclusion. 4. Global rotation or vorticity. Sometimes the idea of a rotating universe appears in public conversation. In serious cosmology, global rotation is constrained and would show up in multiple ways. So if you ever hear the universe is rotating as a definitive statement, it is best treated with caution. It may be a hypothesis, not an established result. 5. Exotic selection effects misread as physics. This is the boring option and also often the most likely. The anomaly is a composite of subtle biases across catalogs that is hard to fully capture. Boring options are not disappointing. They are part of how science stays honest. Now, how do we evaluate these hypotheses? We look for cross-consistency. If a dipole excess is real and intrinsic, it should appear across many independent tracers, radio galaxies, infrared quasars, optical galaxies, and clusters. It should also have a redshift dependence consistent with the mechanism. For example, a local structure explanation should diminish as we go to higher redshifts. A superhorizon gradient could persist. A selection function artifact might correlate with survey depth patterns. So the right question is not simply, is there an anomaly? The right question is, what is the pattern of the anomaly across tracers, redshifts, and methods? This is why recent work emphasizes multi-survey comparisons and careful tension quantification rather than single-number headlines. Now, at this point, you might be wondering, is there a chance this becomes one of those forever anomalies that never resolves? It's possible, but there is also a reason to be optimistic. Astronomy is entering an era of enormous surveys with better calibration, deeper catalogs, and broader wavelength coverage. That means many of the older limitations that complicate dipole measurements are slowly being addressed. So the dipole anomaly is not just a philosophical puzzle, it is a practical target for the next decade. If you'd like to engage here, which kind of explanation feels most plausible to you right now? Systematics, local structure, or something deeper, assuming we keep all conclusions tentative? Comment below with your intuition. Now, in the next file, we will talk about the difference between amplitude and direction. Why direction agreement can be easier to get than amplitude agreement, and why that matters for interpretation. Let's continue slowly. There is also a delicate point about language. When people say new physics, it can sound like a dramatic discovery. But in cosmology, new physics often begins as a tiny correction, a small term that becomes necessary because data refuses to align perfectly. So even if an intrinsic dipole existed, it might not look like a cinematic revolution. It might look like a modest preferred direction that shows up only in the most sensitive statistics. Some theoretical ideas that have been discussed, always cautiously, include early universe mechanisms that slightly break statistical isotropy, inflationary scenarios with vector fields that imprint directionality, or large-scale modes that modulate density across our observable patch. These ideas are not mainstream conclusions. They are proposals tested against constraints. And constraints are strong. The CMB, large-scale structure, and other observables tightly limit how anisotropic the universe can be without leaving broader fingerprints. So any intrinsic dipole explanation must be both subtle and consistent. This is why many researchers prefer to first exhaust the conservative landscape, survey systematics, selection function uncertainty, and clustering modeling. that conservative work is not less exciting. It is the discipline that keeps the field reliable. Now, let's return to something tangible. How do we judge whether a proposed explanation is plausible? We ask whether it predicts additional patterns. For example, does it predict a specific redshift evolution of the dipole amplitude? Does it predict differences between tracers with different bias? Does it predict correlated signals in lensing, in CMB aberration, or in other large-scale asymmetries? If an idea predicts nothing beyond the dipole is bigger, it is hard to test. If it predicts a broader pattern, it becomes scientific. In the next file, we will focus on the idea of prediction and stability, and why direction is easier than amplitude, both for physics and for systematics.
A dipole has two main properties: direction and amplitude. In many discussions of the cosmic dipole anomaly, the direction looks reassuring. It often points close to the CMB dipole direction. That can feel like a comforting confirmation. See, it's our motion. And it might be. But direction agreement by itself is not a complete verdict. Here's why. Many large-scale gradients, including survey systematics, can align with the CMB dipole direction simply because the sky is not uniform in ways that correlate with observing patterns and masks. Also, local structure contributions can have preferred directions related to our cosmic neighborhood. So direction agreement is important, but not decisive. Amplitude is often the sharper test. Amplitude asks, how strong is the forward-backward asymmetry? If amplitude is consistently higher than kinematic expectations across multiple independent tracers, that becomes harder to dismiss. But consistently is a high bar, because amplitude estimates can shift with flux cuts, mask choices, and clustering models. This is why recent literature emphasizes cautious tension quantification and reassessment, rather than assuming early high significance claims are final. Now, let's discuss a related idea that often appears in this debate: the kinematic expectation itself. To compute how big the kinematic dipole should be in a given catalog, you need to know the velocity from the CMB, how Doppler boosting changes flux, how the number counts change with flux, and the typical spectral behavior of sources. Small uncertainties in these inputs can shift the predicted dipole. For radio sources, the slope of number counts and the spectral index distribution matter. For quasars, selection in color space and photometric uncertainties matter. For different wavelengths, different systematics matter. So some of the tension can come from uncertainty in the prediction, not only the measurement. Now, another nuance: redshift weighting. A catalog that includes many low redshift sources is more sensitive to local structure. A catalog dominated by high redshift sources should be less sensitive to local structure, but may be more sensitive to selection function gradients. So the best dipole tests often use multiple subsamples: bright versus faint, high redshift versus low redshift, different sky masks, different cuts. If an excess dipole persists across many subsamples in a stable way, confidence grows. If it shifts dramatically with modest changes, caution grows. This is exactly the pattern that makes the cosmic dipole anomaly scientifically interesting. It is sensitive and therefore informative. Now, to keep our tone restful, let's zoom out. Why does this matter? Because isotropy is not just a philosophical statement. It is embedded in how we extract cosmological parameters. If isotropy were strongly violated on large scales, it could bias interpretations of large-scale structure measurements, dark energy constraints, and even aspects of inflationary initial conditions. But we should be precise. No one credible is claiming that isotropy is obviously and definitively broken based on dipole work alone. The more reasonable statement is dipole tensions motivate careful testing of the cosmological principle with independent data, and that is healthy science. Now, there is also a quiet aesthetic dimension. The cosmological principle is one of the most elegant ideas in physics, that we do not occupy a special place and the universe does not prefer a direction. If there were a preferred direction, it would be profoundly interesting, but extraordinary implications require extraordinary care. So the episode's emotional stance is not alarm, it is patience. Now, in the next file, we'll talk about specific near-term and medium-term observational paths forward, how upcoming surveys can reduce systematics and clarify whether the anomaly persists. If you are still awake, here is an engagement question. Do you prefer scientific mysteries that may resolve cleanly, or those that might remain ambiguous for a long time? Tell me in the comments. I'll shape future episode pacing accordingly. Now, let's look ahead to the instruments and surveys that may help us settle this tension more cleanly than older catalogs could. There's another quiet reason direction can be easier than amplitude. Many estimators, especially on partial skies, can have directional biases. For example, masks and survey boundaries can influence which direction the estimator prefers, simply because certain directions have more uncertainty than others. This means that the direction matches the CMB can sometimes happen even when the underlying causes differ. Amplitude, on the other hand, must fight a harder battle. Amplitude is where calibration gradients, threshold effects, and clustering uncertainty tend to show themselves. So, if future work tightens amplitude estimates in a way that remains elevated across independent surveys, that would be more informative than direction alone. Now, let's also say something reassuring. Even in a perfectly isotropic universe, with perfectly standard physics, we still expect a dipole because we are moving. So the presence of a dipole is not an anomaly. The anomaly, if it exists, is only in the mismatch between expectations and some measurements. That distinction matters. It keeps us from confusing isotropy exists with isotropy is broken. Motion creates anisotropy even in an isotropic cosmology. So the dipole anomaly is not a paradox. It is a precision tension. And precision tensions are how fields improve. Now, in the next file, we'll look ahead to the surveys that may help settle this tension more cleanly than older catalogs could. One of the most comforting things about astronomy is that it is not only theory, it is a steady flow of new data. And the cosmic dipole anomaly is the kind of question that can benefit from that flow. Because dipole measurements improve when catalogs get larger,
calibration gets cleaner, sky coverage becomes more uniform, and multi-wavelength cross-checks become routine. So what are the paths forward? First, better radio surveys. Radio dipole work has been limited by older survey systematics and incomplete sky coverage. Newer surveys, improved processing, and future instruments are expected to deliver cleaner all-sky maps with better uniformity. With more sources and improved calibration, the uncertainties from shot noise shrink, and the ability to model clustering improves. Second, optical surveys with stable calibration. Large optical surveys with uniform imaging help map galaxy distributions with fewer large-scale gradients. They also help because they provide cross-matches and photometric redshifts that refine selection functions. Third, infrared catalogs with improved classification. Infrared selection can reach high redshifts, but it must manage stellar contamination and scanning strategy effects. New catalogs and improved classification methods can reduce contamination gradients that might mimic a dipole. Fourth, lensing and the mass distribution. Galaxy catalogs trace luminous matter, but gravitational lensing can trace the integrated mass distribution more directly. If there were a true intrinsic matter dipole, lensing might eventually offer an independent angle, though lensing measurements bring their own challenges. Fifth, multi-tracer consistency. In the long run, the best tests do not rely on a single catalog. They rely on agreement among many tracers: radio galaxies, infrared quasars, optical galaxies, and clusters. If all these point to the same excess amplitude after robust systematics modeling, the case strengthens. If only some do, the case weakens. Now, it is worth noting that the community has already moved into this phase, reassessing earlier results, quantifying tension with more careful statistical frameworks, and comparing surveys in a more standardized way. That's a sign of maturity. Now, what would a convincing resolution look like? There are several possibilities. Resolution A: systematics dominate. As survey modeling improves, the observed matter dipole amplitudes become consistent with the kinematic expectation within uncertainties. The anomaly fades. Resolution B: a modest residual remains. After improvements, the excess amplitude reduces but does not disappear. It becomes a smaller, persistent tension that motivates further study. Resolution C: a strong multi-tracer anomaly emerges. Independent tracers converge on an amplitude clearly inconsistent with kinematic expectations with robust systematics control. That would demand new theoretical work and deeper tests. At present, the cautious scientific stance is that we are somewhere between A and B depending on tracer and method. But we should label that as an interpretation, not a conclusion. Now, there is a final quiet point that often gets overlooked. Even if the dipole anomaly persists, it might not mean the universe violates isotropy in a dramatic way. It might mean our local motion is more complex than assumed, or that we are not sampling the rest frame in the way we think, or that subtle selection effects persist. The difference between a measurable dipole tension and a broken cosmological principle is large. So we keep the words careful. Now, in the next file, we'll return to the why it matters question, but in a gentle way.
we'll talk about the cosmological principle as a tool and what it means to test a tool rather than cling to it. If you are still awake, here's an engagement question. Would you rather science stay quiet about uncertainties until they resolve, or would you rather hear them early, clearly labeled as tentative? Comment below. It helps me calibrate the integrity style of the channel. Now let's move into a calm philosophical layer. What isotropy means and what it means to test it. A useful way to think about the next decade is this. The sky is becoming a time lapse, and our catalogs are becoming more cross-validated. Radio surveys will be compared to optical surveys. Optical surveys will be compared to infrared surveys. Infrared surveys will be compared to X-ray catalogs, and the overlaps will grow. This is a new kind of strength, because when you can measure the same large-scale pattern in multiple ways, you can isolate what is cosmic from what is instrumental. Even if you don't name every instrument in a narration, the principle is simple. Independent systematics are the best antidote to false certainty. And there's another benefit. As catalogs grow, the statistical width of the expected dipole distribution shrinks. That makes it easier to tell the difference between an unusual but possible measurement and a truly inconsistent one. Still, we should keep one more quiet truth in mind. Bigger data doesn't automatically mean cleaner answers. Bigger data can also reveal subtle systematics that smaller data could not expose. So, the path forward is not only more sources, it is better understanding. Now, in the next file, we'll return to the cosmological principle and treat it like a tool. Tools can be refined. Tools can be replaced, but tools are not moral truths. Let's close our hands gently around that idea.
The cosmological principle is often described as a belief, but in practice, it is a working assumption. It is a lens we put on the universe because it makes the math tractable and the interpretation coherent. And like any lens, it should be tested. The cosmic dipole anomaly is one such test. If the universe were wildly anisotropic, we would expect many obvious directional signals across cosmology. We do not see that in an overwhelming way. So the current question is not, is the universe completely different in one direction? The question is more refined. Are there subtle, measurable departures from perfect statistical isotropy that matter for precision work? This is a quiet, grown-up question, and it fits the modern era because cosmology has become a precision science. When you measure parameters to a few percent or better, small anomalies matter, not because they overturn everything, but because they can bias inference. So, in a sense, the dipole work is a quality control check. Now, there is also a deeper layer. The CMB dipole is interpreted as kinematic, but even that interpretation has a subtle assumption that the dipole is not significantly contaminated by intrinsic large-scale anisotropies. Most evidence supports the kinematic view, but careful scientists still ask, could any intrinsic contribution exist? If so, how would we know? This kind of thinking is not skepticism for its own sake. It is how robust models are built. Now, in recent years, the dipole discussion has been sharpened by the availability of large catalogs and better statistical methods,
including review-level syntheses that lay out the tension, the uncertainties, and the alternative interpretations without sensational language. That is the tone we are following. Now, let's also acknowledge an emotional fact. Humans like symmetry. We like the idea that the universe is the same everywhere because it makes us feel less special and more connected. A preferred direction can feel unsettling, like a cosmic imbalance. But there is no need to make it dramatic. Even if a subtle preferred direction existed, it would not make the sky dangerous. It would simply mean the universe has a feature we did not fully account for. Science has adapted to such features many times before. Now, it may help to picture what anisotropy could look like without turning it into a story of conflict. Imagine the universe as a very large ocean. Isotropy is the idea that far from shore, the ocean looks statistically similar in every direction. Anisotropy, in this analogy, could be like a gentle current, a slow drift that has a direction. A current does not break the ocean, it is part of the ocean. That is the calm way to hold the concept. Now, we are nearing the end of this episode, and we can prepare a clean summary. What is established and what remains speculative. But before that, one more gentle engagement question. If future surveys confirmed a small, real dipole excess across multiple tracers, would you find that more exciting or more unsettling? Comment below. I read those responses carefully because the channel is designed to be both truthful and sleep-friendly. Now, in the next file, we'll summarize the most responsible story, what we can say with confidence and what we should label as uncertain. Another calm concept that belongs here is cosmic variance. Cosmic variance is the idea that we observe only one universe, one realization of the underlying statistical laws. Even if the universe is statistically isotropic, our particular observable patch may have mild features that look like patterns. This does not mean the laws are wrong. It means the sample is finite. For very large scales, cosmic variance is a fundamental limit. That is one reason the dipole discussion can remain subtle. It lives at the largest scales. Now, a careful listener might ask, if cosmic variance is unavoidable, can the dipole anomaly ever be solved? The answer is that it can be clarified. We might not get a perfectly sharp final verdict, but we can learn whether the tension is driven mostly by catalog systematics, by local structure, by statistical fluctuations, or by something more persistent. That kind of clarity is meaningful, even without drama. Now, as we approach the summary, keep this channel's promise in mind. We are not here to sell certainty. We are here to offer calm, accurate perspective. So, let's summarize with that integrity. There is also a practical reason cosmologists care about rest frames. When we say the CMB rest frame, we mean the frame in which the microwave background looks on average as isotropic as possible after removing the dipole. When we say the matter rest frame, we mean the frame in which the distribution of distant matter tracers looks as isotropic as possible in the large-scale limit. In a perfectly standard picture, these frames should agree in the large-scale limit. But in real data, the process of making something look isotropic depends on the tracer you use, the redshift range, and the survey's imperfections. So part of the dipole discussion is almost like comparing two clocks. Both clocks are good,
but if they tick at slightly different rates, you need to ask whether one clock is biased or whether your assumptions about the clocks need refinement. There is also an important supporting observation often mentioned in technical discussions. Our motion relative to the CMB is not inferred only from the dipole amplitude. It is also reflected in more subtle ways through aberration and boosting effects imprinted on the smaller scale CMB anisotropies. These higher-order signatures are harder to measure, but they tend to be consistent with the same basic motion picture. That consistency is one reason the kinematic interpretation of the CMB dipole remains widely accepted. So the current tension is not, is the CMB dipole real? It is, do matter tracers behave exactly as expected once we account for everything that makes surveys imperfect? That is a quieter, more technical question, and it's the kind of question that gets answered slowly with better catalogs and better modeling, not with dramatic declarations. Now, with that context, we can end with a clean, careful summary.
Let's gather the quiet facts. What is established with high confidence? First, the cosmic microwave background has a strong dipole pattern, and the standard interpretation is that it is primarily due to our motion relative to the CMB rest frame. Second, our motion should produce a kinematic dipole in the observed distribution of distant sources through aberration and Doppler boosting effects. Third, real surveys of galaxies, radio sources, and quasars can measure dipole-like anisotropies, but those measurements include multiple components: kinematic, clustering, and survey systematics. Fourth, some analyses have reported dipole amplitudes in matter tracers that appear larger than the kinematic expectation derived from the CMB, with the level of tension depending on tracer and methodology. Fifth, the significance and interpretation of any excess is sensitive to how clustering and systematics are modeled, and ongoing work includes reassessments and more careful tension quantification. That is the sober map. Now, what remains uncertain? Uncertain point 1. How much of the measured matter dipole amplitude is due to unmodeled or underestimated survey systematics? Uncertain point 2. How large the intrinsic clustering dipole is in each catalog given redshift distributions and sky masks? Uncertain point 3. Whether, after fully accounting for systematics and clustering, a statistically significant residual excess remains. And if a residual remains, another uncertainty appears. What physical mechanism, if any, is responsible? At this stage, any claim that isotropy is definitely broken would be too strong. The more accurate stance is, dipole tensions motivate careful testing of isotropy with improved data. Now, this is the part that can feel calming. Science is not threatened by uncertainty. Science uses uncertainty as a compass. When a measurement is difficult, researchers build better tools. They run better simulations. They collect more data. They compare independent methods. Over time, the uncertainty landscape becomes clearer. That process can be slow, but it is steady. And in cosmology, steady is a virtue. Now, if you are still awake, here is one final engagement question before we close. Do you want future episodes to include short mentions of specific surveys and papers by name, or do you prefer the narrative to stay more general and meditative? Comment below with your preference. Now, in the final file, we'll close gently, keep the tone sleep-friendly, and transition into the next episode in the sequence you chose. And because this is a YouTube channel, it's worth adding one more integrity note. When you describe this topic in titles, thumbnails, and intros, it helps to keep the framing honest, as a tension in dipole measurements, a precision test of isotropy, what surveys may be telling us, rather than anything that implies hidden secrets or absolute proof. That kind of phrasing is not only more accurate, it is also safer for audience trust. If you choose to add a short disclaimer in the video description, a simple line is enough. This episode includes AI/CGI scientific visualizations for illustration. It is not real footage. That keeps the viewer oriented without breaking the calm mood. Now we're ready to close. One last question, very gently. Do you feel more comforted by the idea of a perfectly uniform cosmos, or by the idea that the cosmos can still surprise us? If you want, leave a short comment. Even a single word is enough.
As we close, let's hold one simple line. A dipole tension is not a verdict, it is a question. The cosmic dipole anomaly asks whether the rest frame defined by the CMB aligns perfectly with the way matter appears on the largest accessible scales. Some measurements suggest a tension in amplitude. Other analyses emphasize the role of clustering and systematics. The story is still being refined. What we can say without stretching the truth is this: the universe is consistent with isotropy on large scales in many ways, but precision tests continue, and dipole measurements are among the most sensitive. So tonight we did what calm science does. We separated what is well supported from what is still uncertain and from what is speculative. And we stayed gentle with the words. If you enjoyed this sleep-friendly cosmic documentary, you can support the quiet universe in a simple way. You can like the video so it reaches more listeners who want quiet science at night. You can subscribe so you don't miss the next episode. And if you know someone who relaxes best with calm space stories, you can share this episode with them. No pressure, just a quiet invitation. In the next episode, we'll move to another modern frontier, gravitational waves, and listen to what a new era of detections might be whispering about black holes and neutron stars. For now, let the sky soften. Imagine the dipole as a gentle gradient of warmth and coolness across a dark sphere. Not a conflict, just a subtle motion. One slow breath in, one slow breath out. And if a thought arrives, you can let it drift like a distant galaxy, faint and harmless, passing gently across your attention. And for those who like a final image to fall asleep with, here is one. Picture a sphere of night. On one side, the tiniest hint of warmth. On the other, the tiniest hint of cool. Not a dramatic contrast, not a battle, just a gradient, the signature of motion. Now picture the matter in the universe. Galaxies like faint lanterns scattered through an enormous volume. If you drift through them, the lanterns subtly crowd ahead of you and thin behind you. A dipole appears, quietly, inevitably. And then, because the universe is not perfectly smooth, the lanterns also cluster. Some regions are dense, some are empty. So the dipole you measure is never pure, it is always mixed with structure. That is why this topic is so soothing in a strange way. It is a reminder that the universe is not obligated to be simple for us. It can be elegant and still be difficult, symmetric and still be noisy, predictable and still be subtle. If you take nothing else from tonight, take this. Precision is hard, and careful language is part of precision. Now, as promised, we will continue the new sequence of episodes you selected. Next up, the new era of gravitational waves, where the universe doesn't just shine, it vibrates. Until then, thank you for spending this quiet hour with the quiet universe. Like, subscribe, or share if it helps others find calm science at night. And if you want, leave a comment with the one word that best describes how this episode felt to you. Now, let your attention loosen. The dipole fades. The star field softens. And the night becomes simple again. And if you'd like to carry a final thought into sleep, let it be this. The universe is allowed to be both simple and complicated. Simple in its laws, complicated in its measurements. When we measure, we bring instruments, thresholds, masks, and choices. We bring our location in a clumpy cosmic web. We bring noise. We bring the fact that we only see one sky. So attention can appear even when the underlying model is right. And sometimes attention can remain because the model needs a small new ingredient. The honest posture is to hold both possibilities without rushing. Now, a quiet preview of the next episode in your sequence. We'll talk about gravitational waves, the way space-time itself carries information. We'll keep the same calm tone, a short, honest hook, clear framing, and a careful separation between what is established and what is still speculative. For now, let the dipole drift out of focus. Let the questions become soft, and let the night do what it does best. And if you're the kind of listener who likes a small ritual, choose one quiet sentence from tonight. Attention is a question, and let it repeat slowly in your mind. Not to solve anything, just to soften the edges of thought as you fall asleep. Sleep well, and I'll see you in the next quiet sky. Good night.